Okay, so welcome to the AC Final Study Guide for ICW. This is going over everything we've gone through in AC class this semester, between the basics of trigonometry to the basics of alternating current, inductors and inductance, capacitors and capacitance, reactants, RL, RC, and RCL circuits, all that good stuff. So let's just get going. Sorry. So trigonometry basics. Trigonometry is essentially the math behind calculating right triangles. So right triangles consist of two sides forming a right angle, the hypotenuse, which is the line connecting the 2 points of the sides. Two acute angles. Acute angles are below 90 degrees, and the right angle, which is obviously 90 degrees. So the hypotenuse of a triangle is always the longest side of the triangle and found by finding the square root of both sides, multiplying them, and sorry, I should have said by finding the square of both sides, adding and finding the square root of the resulting number. Calculating the acute angles of the triangle are done by dividing one of the sides by the other, depending on which function you use. So sine uses the opposite in the hypotenuse. Remember, the opposite is the one that's not touching the angle, or as Angelia says, if you would draw a straight line out of the angle, the other line would be quote unquote bisected by it, which essentially means cut in half, is an easy way to think about it. The cosine uses the adjacent side, so with these angles, you're going to have two sides that touch it. The hypotenuse is obviously the largest side, and then your other two sides, obviously. So this is using both of the sides that touch the angle, but specifically the adjacent over the hypotenuse. And the tangent uses the opposite over the adjacent. So you can use the SOHCAHTOA to remember it. Sine opposite hypotenuse, cosine adjacent hypotenuse, tangent opposite adjacent. Pretty simple. Find missing sides. When you have an angle in another side, you need to isolate the variable. So this is something we went over in math class, but basically you need to figure out how to get the variable on its own. I went through this here using 12 inches and 45 degrees. Just a little bit long-winded, so we're just going to skip it for now. If you need to, pause the video and go through this. Feel free to make your own practice problems, whatever. The basics of AC. So AC stands for alternating current, which is the opposite, not opposition, of DC or direct current. As AC can move both forwards and backwards in a circuit compared to direct current, which only goes one way. The advantage of AC is that it can be transformed into DC in a process called rectification using diodes, and AC volts can be transformed easily to increase or decrease. You can only use AC going into a transformer. AC is measured using sine waves, which are waves displaying the changes between various points, and AC sine waves are most commonly measured using an oscilloscope. Oscilloscope. Which that's how you measure it to get a visual representation. Otherwise, if you're just trying to measure the voltage itself, obviously you just use a meter. Yeah. So your peak voltage in a circuit is the highest amount of voltage it will produce at any one side, either pole. Your peak to peak is the difference between your voltage at your two greatest points. The RMS, which stands for root mean square, is the effective voltage in an AC current, average is the voltage if it would be turned into DC, and half wave average is the DC voltage that you would get if you only took the volts above ground from your AC. So for example, using this chart here, a full wave would stay up here, but before it goes below ground, it would go back up again, compared to a half wave would just lose this section here. Yeah, it displays the relation between RMS peak and peak to peak. Obviously, peak to peak, it's just your peak twice. Actually, I have another slide for this. So the RMS is found by multiplying your peak by 0.707, which is what the root mean square stands for. It's essentially the square root of 2. Or you can find your RMS by using your average and multiplying that by 1.1. Your peak can be found by multiplying your RMS by 1.414, or the square root of 2. Your average can be found by multiplying RMS by 0.9, or 90%. And your peak to peak is found by multiplying your peak by 2. Now, technically, there is formulas to find your average using your peak, but personally, I would rather take the extra step to make sure that I do it right, instead of having to remember more numbers, if that makes sense. So AC power going through a circuit completely, like going out and returning, is called a cycle. Now, the frequency of a circuit is the measurement of the amount of cycles completed in 1 second. The common frequency within the US is 60 hertz, but in other parts of the world it's commonly 50 hertz. And in these AC circuits within the conductors, electrons are forced to the outer edges of the conductors by eddy currents, causing what is known as the skin effect. I ran out of space to put that somewhere, so it's just kind of at the end there. Induction. Induction is the creation of electromagnetic force, or voltage, by passing a conductor through a magnetic field. Polarity of induced voltage is dependent on the magnetic field itself and the movement of the conductor. And this is remembered using Fleming's left-hand rule, which is displayed at the bottom there. The movement of your thumb determines the movement of the conductor. The movement of your index finger, or your first finger determines the movement of the magnetic field itself, which way it's going. And the middle finger represents which way through the current, or through the conductor, the current is going. Induction is usually achieved using a coil of wire and a magnet, or some sort of magnetic material. Like, for example, we had a display in lab where Troy energized a roll of wire and put a piece of EMT through the center to induce a current. The amount of induced voltage is determined by the number of conductors in a coil of wire. The amount of turns of conductor in a coil of wire, the strength of the magnetic field, and the speed at which the magnetic core cuts lines of flux. So the cutting motion itself is what causes the voltage. This is called Lenz's law, and induced current does not generate instantly, as current comes from the expanding of a magnetic field, which does not happen instantly. The current from the generated field scales exponentially over a period of time consisting of 5 sections, with a constant of 63.2% of progress made per constant. So, if an inductor produces 1 amp of current in the first time constant, it would generate 63.2% of that current. The second time constant would be the 63.2% plus 63.2% of the remaining current to be generated, essentially. So, inductance is measured in henries, and the Henry value of an inductor is found using this formula here, which essentially what it's saying is 0.4 is your constant. Pi is the diameter. It it's a symbol that's used for calculating circular area and stuff like that. Yeah. N is for the number of turns of wire, which you then square. The micro symbol is the permeability of the core of an inductor, which you would be given normally. A is the cross-sectional area of the core, and I forgot to add this, but the lowercase l here is the length of the core itself. So, RL time constants is the formula used to figure out how long it would take for an inductor to reach maximum current using inductance divided by wire resistance to find one time constant, which is used to find the total time by multiplying by 5. So, inductance in AC circuits. So, inductors in AC circuits cause induced voltage, which is 180 degrees out of phase or opposite to your applied voltage. Induced voltages oppose changing currents that create them. They are calculated using the resistance of the inductor wire and the amount of amps flowing through it, which is just Ohm's law. And the resistance of inductors is called inductive reactance, which is calculated using 2 pi FL, where F is frequency, L is inductance. You can find your L by dividing XL by 2 pi F, and you can find F by dividing XL by 2 pi L. Inductors act similar to resistors in circuits. When connected in a purely inductive series circuit, the total inductive reactance and total inductance is found by adding your values together. So if you have multiple inductors in a circuit, and when connected in a purely inductive parallel circuit, you find it by using the whole inverse over inverse thing that we use for calculating most resistances in parallel. In purely inductive circuits, applied voltage leads your current by 90 degrees and induced voltage lags your current by 90 degrees. In a purely inductive circuit, your power is called VARs, which is found by multiplying your induced voltage by your current. VARs are also called reactive power and are also used in capacitive circuits. So, I went a little bit out of order here. So right now we're at capacitors, because inductors and capacitors are very similar. So, capacitors are made from two differently charged plates separated by a dielectric material and act as batteries in circuits, essentially. They are used to store charge, basically. They are charged by a power source and hold charged particles in their plates. When not being charged, capacitors hold most of the charge but lose some particles to leakage current. And when charged, the atoms in the dielectric become stretched and their outer ring of valence electrons become stressed, which is known as dielectric stress. Capacitors are measured in capacitance, which is measured in farads. Capacitance is represented by C and is basically the opposite of Henry's and your inductance. The total capacitance in a circuit is calculated the same as inductance, inductive reactance, and resistance. Meanwhile, the capacitive reactance, I think I wrote that down wrong. What I mean to say is your total capacitive reactance in a circle is calculated the same as your other resistive loads, resistive, reactive, or inductive, etc. And your capacitance is found the opposite of inductive reactance and resistance. So essentially what that's saying is, in a series circuit, you're going to find your capacitance like you would find your resistance in a parallel circuit, and vice versa. You're going to do that inverse addition thing. Capacitors charge and discharge at an exponential rate identical to inductors generating a magnetic field. These time constants are called RC time constants and are calculated by multiplying the resistance of the circuit or resistors in a circuit by your capacitance. I forgot to finish that, my bad. The value gotten would then be multiplied by 5 to represent the 5 total time constants, or the total time it takes to charge and discharge. Capacitors come in either polarized or non-polarized versions. Non-polarized can be used in AC or DC circuits, as because they're non-polarized, they can flow in either direction. They're commonly known as wet capacitors, which contain oil, similar to transformers. And they're usually used in motor circuits and power factor correction. The only real downside to them is that they can leak current a bit more, I believe. And polarized capacitors can only be used in DC and must be used according to markings in relation to the polarity of the capacitor. Polarized capacitors are also known as dry type and have a lower chance to leak current. Again, dry type and wet type are similar to transformers. That's kind of an easier way to think about it. Variable capacitors function similarly to variable resistors, changing the capacitance value according to input. So, how we work with, potentiometers and rheostats and all that good stuff. You can change it on the fly, essentially. And certain capacitors, specifically ceramic capacitors, are rated based on their value, which is determined by marks on them identical to resistors with the black, brown, red, orange, yellow, green, blue, violet, gray, white, 0 to 9 system. So it's the same as what we did with resistors last year. Okay. Capacitive circuits. Capacitors create capacitive reactance, which is similar but opposite to inductive reactance. It's calculated the same, but the answer you get when you calculate it, when you do the 2 pi fc, you need to then invert it, because otherwise you're going to be left with a very small number. In purely capacitive circuits, current lags the applied voltage, which is opposite of the inductive circuits. I think that's correct. Capacitor voltage ratings need to be considered when using a capacitor in an AC circuit, as the rating is for the peak voltage of the circuit. So if your circuit is 240 volts, your peak of that circuit is 340 volts. So then if you put a 300 volt capacitor in, it would break it. Most parts of a capacitive circuit are identical to an inductive circuit except for the capacitance itself. So, like I said earlier, in a series circuit, capacitance is calculated like you would do resistance in a parallel, and in a parallel, it's calculated like how you would do resistance in a series. And capacitive reactance is identical to resistance in parallel and series. So, the way to think about it is that your inductance and then all three of your types of resistances, your two reactances and your actual resistance, are going to be calculated the same, and only the capacitive is different, or capacitance is different. So RL series and parallel circuits. So RL circuits are circuits containing both a resistor and an inductor. In both circuit types, you calculate all your values the same using Ohm's law and the formula for inductance and inductive reactance. So, for voltage, it's I times R. For amps, it's E divided by R. For watts, it's E times I, etc. However, your impedance, your total voltage, your total amperage, and volt amps are calculated using trigonometry depending on how you have it set up. I'll go into it in a minute here. And then the phase angle of RL circuits is always positive. So, to find the voltage in an RL series circuit, you find the voltage drops across all inductors and resistors and total them up into the total inductive voltage drops and resistive voltage drops. You then use these to create a triangle with them as your sides, and then you do the method to find your hypotenuse. You do the a squared plus b squared equals c squared, or c equals the square root of a squared plus b squared. So, yeah, you guys should know how to do basic Pythagorean theorem at this point. Um, you would use the same method for impedance and voltamps, but your amperage obviously remains the same across the entire circuit because it is a series circuit. And you can find your totals using any other totals by using standard Ohm's law formulas. So for example, if you don't feel like going through this method to find your impedance, but you have your amperage and your voltage, or even just like your amps and your watt, or your VA, or your volts in your VA, you can do your standard Ohm's law calculations to find those. In parallel circuits, it's similar but different. With amperage, you would find it the same way you would do for your voltage in a series circuit, where you find your amperage drops across inductors and resistors, and then you use that to find your hypotenuse of a right triangle. Impedance is done different. The method that I listed first is pretty complicated. The way that they explain it in the book doesn't make a lot of sense. But basically, how it works is you find your total resistance and your total inductive reactance the same as you would in any parallel circuit. You do the inverse method. But then to find your total impedance, you do, like, I think it's, you take your inductive reactance inverse plus your resistance inverse, you find the square root, or it's complicated, and I listed it out as easy as I could in here, but it's just a lot to go over, and it's not as easy compared to just doing the Ohm's law formula, which as soon as you find your voltage and amperage, voltage and wattage, amperage and wattage, any of that, you can find your impedance all the same. Your voltage remains the same across the entire circuit, and your VA is found with your wattage triangle with watts and bars. Pretty simple. So RC series and parallel are identical to RL series and parallel, aside from your capacitance. Again, in series, your capacitance is counted as a parallel would be, and in a parallel, it's counted as a series would be for other resistors. You should get it by now. The big difference is that in RC circuits, the phase angle is always negative. So RCL circuits, so this is inductive, resistive, and capacitive all together. Now, in these circuits, capacitance and inductance work against each other. So a circuit can only be more capacitive or more inductive. It's always going to be resistive if it has all three items in it. It's just that it's going to be more capacitive or more inductive depending on which value is greater. So yeah, you find your values. So you would find your voltage drops, your amperage drops, your reactance, your VARs, whatever, and you take the smaller one, subtract it from the greater one, and then whichever one is greater is what you go with. So for example, if I had 800 capacitive VARs versus 600 inductive VARs, that leaves me with 200 total VARs, and it would mean that my circuit is more capacitive, so my phase angle would be negative. It's just your capacitance and your inductance fight against each other, and which one is more powerful determines your phase angle. That's about as simple as I can get it. It's kind of, it's pretty damn simple, all things considered. I'm not going to repeat myself another time. You guys should get it, hopefully. I'll be making another one of these for Blueprint soon, so let me know if you have any questions, and best of luck on the test. Thank you.